great speaker with exciting results. So yeah, it should be a scintillating non-nap after lunch. Thanks so much, Andras.
Yeah, thank you, Dorothy, for the invitation. So I'm going to talk about cobordism maps in not Floer homology. And here I also think of link Floer homology. And as Dorothy mentioned, this is joint work with Marco Marengon, who's here. So I'm first going to define what a decorated link is. And it's a triple YLP. So this is a decorated link. And I'm just going to basically draw a picture. So you have a link in your close connected oriented three-manifold Y. So this is your link L. And you have a positive even number of marked points on each link component. So these are the points P. And then I'm going to label the complementary arcs by plus and minus in an alternating way. So the link is then the union, and I denote it like R plus of P union R minus P. And so P is the intersection of R plus P and R minus P. So this notation was motivated by Gabai's sutured manifold theory. And I'm going to also consider cobordisms between decorated links. And so this is a triple X, F, and sigma. This is a decorated link cobordism from, say, Y0, L0, P0 to Y1, L1, P1. If, so first I'll draw the picture. You have your two decorated links. Suppose that this is a two-component link here. Here you have Y0 and here you have Y1. And this is your link L1. This is the link L0. And then I have a cobordism X between these two three-manifolds. It's an oriented cobordism. And inside I have some properly embedded oriented surface. That's a cobordism between L0 and L1. I denote this surface by F. And then sigma is some dividing set on this surface. So this is sigma, these properly embedded one manifold. And when I write it down, so XF is a link cobordism from Y0, L0 to Y1, L1. And just like in the case of these dividing points P, so the sigma divides the surface F into a positive and the negative part that I denote by R plus of sigma and R minus sigma. So F is the union of R plus sigma and R minus sigma, and sigma is the intersection of these two subsurfaces. Okay, and the endpoint of sigma separate these marked points P0 and P1 on the link components. So if you take the induce map on the components of the boundary of sigma to the components of L0 minus P0 and L1 minus P1, this is a bijection. It might sound a bit odd that these arcs don't quite end at the points P, but there is some contact topology secretly in the background, and then it makes more sense. And there is an orientation condition, so we can orient every component R of F minus sigma such that when I look at the boundary of the closure of this component, say this component, that this, so when this crosses a point of P0, then it goes from R plus of P0 to R minus of P0. And on the top, it does exactly the opposite. So when it crosses a point of P1, it goes from R minus P1 to R plus P1. And finally, you can have closed components of F, but you have to have some dividing set on it. So if F naught in F is a closed component, then sigma intersected with F naught is not empty. Okay, so that was a rather technical definition, but the good thing is that decorated links with these cobordisms form a category that I denote by D link. So this is the category of decorated links and equivalence classes of decorated link cobordisms. And what I showed is that there exists a functor, the link Floer homology functor, from this category D link to the category of Z mod 2 vector spaces, such that for a decorated link is isomorphic to link Floer homology as defined by Ojvát and Szabó. So really the substantial part of this is that the link cobordisms induce maps, and so given a decorated link cobordism X, I denote by F sub X the cobordism map from HFL hat of L0 P0 to HFL hat of L1 P1, and so this is a linear map. And I should mention that Ian Zemke defined in a different way cobordism maps on other flavors of link Floer homology, such as cobordism maps on HFL plus, minus, and infinity. So based on this construction. Okay, and then the first result that I'm going to talk about today is the grading shift of these cobordism maps. So
Can you just explain where in the wide nature I find such objects?
what do you mean?
Well,
You don't like the decorations, right?
exactly.
I'm going to tell you why you need them, okay?
So that I might understand, but I still don't like them. Like where do we find in nature? Where do we find decorated link cobordisms?
Let me get to some applications, topological applications, and maybe then they will be more appealing.
Okay.
Right, so consider a cobordism where the ambient four manifold is just S3 cross I, and I have a decorated surface inside. Then f of x shifts the Maslov grading so this is the homological grading on this homology theory by the Euler characteristic of f plus the Euler characteristic of R plus of sigma minus the Euler characteristic of R minus sigma divided by 2. So it just depends on the topology of this cobordism, and for the Alexander grading by, so this is just the single variable Alexander grading, not the multivariable one, by the Euler characteristic of R plus sigma minus the Euler characteristic of R minus sigma over 2. And you can notice if you take the difference, then this delta grading and shift only depends on the surface F and not the decorations. Okay. Now, why are the decorations necessary? So here let me state a result that I proved with Dylan Thurston, namely that if YLP is a decorated link, then link Floer homology HFL hat of YLP is functorial with respect to the mapping class group of this data, and in fact if you take automorphisms that move the marked points around the link, they typically induce non-trivial maps on link Floer homology. So Sarkar showed the following, and then there is a general formula by Ian.
Functorial with respect to mapping class, what does it mean? Functorial with respect to?
So these are diffeomorphisms of Y that preserve L setwise and P pointwise.
What does functorial with respect to mean?
So there is an action of this group on.
That's clear to me, okay.
In fact, it's yeah. This is necessary to define a TQFT on such objects. Right. So here is an example of this action. So take a knot K, and take a tubular neighborhood of it. And there are these marked points. Just take 2 marked points. And then take this sort of like a Dane twist or a finger move that twists by 2 pi along k, and is the identity outside this tubular neighborhood. And let me denote the diffeomorphism dkp, so it maps S3kp to itself. Of course, it's isotopic to the identity if you don't care about the base points, but it's not in this group. And so Suture, it computed the action of these maps for knots of at most, I don't know, 10 crossings or 9 crossings. And in this sense, for most, again, this is not a rigorous statement, for most k, the action of dkp is not the identity of hf k hat of k comma p. So to functorially define not Floer homology, at least the hat flavor, and link Floer homology, you need to keep track of the base points. And then when you have cobordism, of course, you again have to keep track of base points. That will give you some decoration. Right, so let's look at a nice class of link cobordisms, namely concordances. So here's the definition. Let's see xf sigma be a decorated cobordism from S3 K0 P0 to S3 K1 P1. And we say that this is a decorated concordance if so I want X to be a homology S2 S3 cross I, H1X, H2X should vanish, and then F is just a cylinder. It's homeomorphic to S1 cross I, and sigma just consists of 2 arcs connecting K0 and K1. Right. So you have 2 knots in S3, K0 and K1. Here you have a cobordism X, and you have some annulus embedded here, and sigma consists of 2 parallel arcs. Right. So here is a remark. You can take the following trivial concordance, where you just take S3 cross I and the knot cross I inside, but then you take non-trivial decorations that wind around the cylinder once, like so. So X is S3 cross I, F is K cross I, and sigma winds around F once. Then, just using standard TQFT arguments, you can show that the map induced by this concordance is the same as this diffeomorphism map dkp star computed by Sarkar. And I should mention Ian Zemke, who gave a general formula for this action. And so this doesn't induce the identity. without the decorations, you cannot make this construction completely functorial. Now, if you specialize this grading shift formula, theorem 1, to concordances, of course, the Euler characteristic of an annulus is 0, and R plus and R minus have the same Euler characteristic. So the Alexander and the Maslov grading shift both vanish. And so this is a corollary of theorem 1. This is something we proved before proving theorem 1, in fact. So if C is a concordance from S3, K0, P0 to S3, K1, P1, so decorated concordance, then FC maps HFK hat sub J of K0, P0, I to HFK hat sub J K1, P1, comma I. Okay, so it preserves the Alexander grading and it preserves the Maslov grading. Now, let's see some topological application of this, and define invertible concordances. I mean, these were introduced by Sumners. So a concordance, and not decorated, just in the usual sense, as in S3 cross IF, from K0 to K1 is invertible if it has a left inverse. So if there exists a concordance S3 cross IF prime from K1 to K0, such that F prime composed with F is equivalent to the product concordance K cross I. And we write K0 less than or equal to K1 if there exists an invertible concordance from K0 to K1. Now, you might immediately wonder whether this is a partial order if I use this notation, and indeed it is. So this is a partial order. And this follows by, for example, noting that if you have this relation, then there is an epimorphism of the knot groups, which is known to be a partial order. Now, the reason why Sumners
Epimorphism by 1, that's not the same as epimorphism by 1, so why do you get in partial order?
I'll tell you afterwards, okay.
Okay.
It's not something you immediately see.
Okay.
It's not completely obvious, that's it. Okay. So, suppose that the unknot is less than or equal to K. So there's an invertible concordance from U to K. Then this happens if and only if K is doubly sliced, i.e., there's a hyperplane cross-section of an unknotted S2 in S3. In S4. And this is a notion introduced by Fox, and it is an interesting problem. What are the doubly sliced knots. Okay, so a corollary of theorem 1, or more precisely the corollary of this theorem 1 that I wrote down. So if k0 is less than or equal to k1, so there is an invertible concordance from k0 to k1, then the dimension of hfk hat sub j k0 comma I has to be less than or equal to the dimension of hfk hat sub j k1 comma I for every I, j in Z. So Floer homology gives an obstruction to finding an invertible concordance. And if you combine this with the theorems that Floer homology detects the genus, so the largest I for which this group is non-zero is the cipher genus, then you get the following corollary. So if k0 is less than or equal to k1, then the cipher genus of k0 is less than or equal to the cipher genus of k1. This also follows from more classical results of Gabai, and furthermore you can, for example, conclude that if k1 is fibered and the genus of k0 is equal to the genus of k1, then using the fact that the top term of Floer homology is one-dimensional if and only if the knot is fibered. Now this condition turns out to be unnecessary, and you can use Stollings's theorem characterization of fiberedness to obtain this result as well. Now another result that I'm going to talk about now is that these knot concordance maps are always non-vanishing. And for this, recall that there is a spectral sequence that starts from hfk hat of S3kp and converges to the Heegaard-Floer homology of the MBN3 manifold, which is in this case S3, and that's just isomorphic to Z mod 2. And the third theorem with Marco is that if C from K0 P0 to K1 P1 is a decorated concordance, then there exists a morphism of spectral sequences that is the knot Cobordism map on the E1 page, which is Floer homology, and is the identity of Z mod 2 on the E infinity page, which is the Heegaard-Floer homology of S3. The morphism of spectral sequences is just a sequence of homomorphisms between the different pages of the spectral sequences, such that if you take the induced homomorphism, you get the homomorphism on the following page. Okay? And so this implies that our maps are all non-vanishing, but slightly more, for which I'll introduce a bit more notation. So let A1 of k comma p be the set of elements of the not-Floer homology hfk hat of k comma p such that x survives every page of the spectral sequence, so it is a cycle, and in the limit it represents the generator of hf hat of S3. Now, this should be familiar from the definition of the Orzsváth-Szabó tau invariant. So they defined tau of k to be the minimal Alexander grading of elements of A1 of kp that are homogeneous. And as you probably know, that this is a homomorphism from the not concordance group and gives absolute value, gives the lower bound on the slice genus. So then a corollary of our theorem 3 is that if C is a concordance from K0 P0 to K1 P1, then you get another proof, that's not the interesting bit, that the tau invariants of the two knots agree, and Fc from the bigraded part 0, 0, hfk0 of k0, p0, tau of k0 is mapped to hfk hat sub 0, k1, p1, tau of k1 is non-zero. Furthermore, Fc maps A1 of K0 P0 into A1 of K1 P1. So it preserves the set of elements that survive the spectral sequence and represent 1 in the limit. Okay. So you can use this to get an invariant for slice disks the following way. So let's take B to be an integer homology 4-ball with boundary S3. And inside, let's take a slice disk. This is just a properly embedded disk. I call it S. So S in B is a slice disk with boundary some knot K in S3. So here you have the knot K. Then we obtain a concordance from this by just taking a point on the disk, removing a small ball that intersects this disk in a small disk. This boundary is an unknot, and removing that ball, and so you obtain a concordance from the unknot to your knot K, and that induces, well, you take some decoration, but it turns out it doesn't matter what decoration you take, because the not-Floer homology of the unknot is just Z mod 2. So you take, say, HFK hat of the unknot, and this is isomorphic to Z mod 2. Inside you take the generator 1, and I map this to the not-Floer homology of the knot K, which gives you a well-defined element in not-Floer homology, and this is an invariant of the sliced disk up to smooth isotopy. Unfortunately, we don't know whether this can distinguish any sliced disks. So I take T as P, P is the decoration on the knot K, to be the image under this concordance of this generator 1, element of HFK hat sub 0 of K P 0. And this is independent of the decoration on the concordancy of S. And the question is, do there exist sliced disks with the same boundary such that these elements are different? And the main issue is that it's not so easy to compute elements of not-Floer homology because you somehow end up using different Hagar diagrams and you have to compare them, and that involves counting various triangle maps. So either way, I would be very interested in an answer to this question. Okay, now, of course, when you are computing cobordism maps, you are interested in what happens when you look at elementary cobordisms. And so, in this case, elementary decorated cobordisms. So some notation. First, let V be this two-dimensional F2 vector space generated by these two elements B and T, and these live in Maslov grading -1/2, +1/2, and Alexander grading 0. And W is a similar vector space, which is generated by little b and little t, and they live in Maslov grading -1/2 and 1/2, and the same for the Alexander grading. Okay, so the following elementary cobordisms generate this decorated link cobordism category. So there is birth, of course, where you have a local minimum on the surface. Oh, so here I focus on the ambient manifold S3 cross I. I call this curly B, and the map, so there might be other link components here. And then here there is an identification between the link Floer homology of L1P1 with the link Floer homology of L0P0 tensor V, where this is a cobordism from L0P0 to L1P1, such that the map is just tensoring with this top generator here. And if you have a death cobordism, which is the same thing upside down, with this decoration, then we can identify L0P0 with the link Floer homology of L1P1 tensor V, such that FD maps X tensor T to 0 and X tensor B to X. Unfortunately, we haven't been able to prove a nice duality result for turning a cobordism upside down, so I do both. Okay, so now, so this is the Then, of course, you can have critical points on the dividing set sigma on the surface. And we called these stabilizations. And these stabilizations, and there are two types depending on the decorations. So a positive or a negative stabilization is when you have product piece of cobordism and you have a local minimum on sigma, and this is positive or negative depending on what the sign is in this little bicon here. So in this case, we can identify HFL hat of LP1, so the link doesn't change. L1 is equal to L0 with HF L hat L, sorry, yes, with LP0 tensor this other vector space W, which is on the right at the top, such that Fx of x, so this is a cobordism x, then equal to x tensor little t if x is positive, the positive case, and x tensor b if x is negative. And similarly, there is a destabilization, positive and negative, which is the same thing turned upside down, and the map is indeed dual. So here we can identify the link Floer homology of L P0 with HFL hat of LP1 tensor W, such that there are, of course, two cases. In the positive case, the cobordism map, so this is again x, maps x tensor little t to 0, and x tensor b to x if x is positive. And the other way around, if x is negative, it maps x tensor t to x and maps x tensor b to 0 if x is negative. So now another thing that you should consider is an isotopy of your link, so no critical points, but you have some isotopy, and this induces some diffeomorphism D, and the map is just the map induced by this diffeomorphism. And finally, of course, the most interesting thing that can happen is a saddle cobordism. And the map actually agrees with the map in the skein exact triangle, except you have to think a bit about what the skein exact triangle looks like when you include the decorations and try to make it functorial. So finally, if you have a saddle, then here's a local picture of your surface. Okay, so here is the saddle critical point of the height function, and here I have a decoration component of sigma like so, and I have a marked point here and here. And so in the projection, not projection, what you see is you have these two marked points, and then after you pass the saddle, you go to here with these decorations. so this is L0, P0, and this is L1, P1. And now let's consider a third link, which is just the following, adding this clasp. Yeah, let me call this LP1. Okay, then there is a skein exact triangle, HFL hat L0 P0 to HFL hat L1 P1, and then the third vertex is HFL hat L P1 and this map here is in the skein exact triangle actually coincides with the mapping used by this saddle. Right. So, and of course the statement is that these elementary cobordisms generate the decorated link cobordism group. So sort of you can compute this map, except of course this involves a triangle count. Now, since I have a bit of time left, I'm going to talk about the proof of this result, this corollary here, about the inequality between the cipher genus following from having an invertible concordance. And put it here. So this is the proof of that corollary that I don't know whether I numbered. Okay, so suppose you have an invertible concordance from K0 to K1, and it's invertible, hence has this left inverse. From K1 to K0. And so this composition is equivalent to the product concordance. So this is here, the cylinder is K0 cross I. And there is a diffeomorphism from S3 cross I to S3 cross I. This is D. That straightens out this cylinder, but then it sort of mucks up this middle level set. So this middle level set goes to some embedded S3 in S3 cross I, but it's no longer nicely embedded. And of course you can take the projection P down into S3. And then you take the this I is the embedding of S3 into this middle level set. And you take the composition, call this map F. So I take the middle level set, then I apply this diffeomorphism D and project it down there. So D is the map that maps F prime cross F to K0 cross I. And it is the identity on S3 cross DI. It also satisfies the property that F inverse of K0 is K1. And so we'd like to show an inequality between the cipher genera of K0 and K1. So I take a minimal genus Seifert surface for K1. So S is a Seifert surface with boundary K1 is a minimal genus Seifert surface. Then goodbye prove the following result. So if you have a 3-manifold and S is a compact oriented surface with connected boundary, and then you have a map from S to M such that F restricted to the boundary is an embedding, and F inverse of F ds is ds, so no interior point hits the image of the boundary, then there exists a surface T which is embedded in M with the same boundary as the image of the boundary of S, and with genus less than or equal to the genus of S. So this is some sort of generalization of the Dane lemma to higher genus surface. It's a deep result of Gabay, and you see it immediately then implies a result because this F that we constructed here restricted to the Seifert surface for K1 satisfies Gabay's theorem, and hence implies the genus of K0 is less than or equal to the genus of K1. So that's a non-Hagar-Floer proof of that corollary on the right-hand side. Now, just to quickly indicate how you prove the other result about fiberedness, so if you take G to be F restricted to the exterior of the knot K1, so this is S3 minus a neighborhood of K1, then this maps the exterior K1 to the exterior of K0 and is a degree 1 map. And hence it follows that it induces an epimorphism between the knot groups. And so it also induces an epimorphism on the commutator subgroups. So this is the commutator subgroup. And then if K1 is fibered, then we know by a theorem of Stolling's that the commutator subgroup of the group of K1 is finitely generated, and so pi1 of E K0 prime is also finitely generated And this is an if and only if statement, so then this implies that K0 is also fibered. And I should mention this alternative proof was communicated to me by Danny Ruberman. Okay, so I think I stop here.
So if you replace the condition that H2 is 0 by H2 is negative definite, then can you do the same?
You mean the non-vanishing result? Which result in?
Yeah, for example, the non-vanishing.
I don't think so.
Yeah,
I don't think so. No.
Yeah, so I just don't know why you need the fact that H2 is non-zero. Sorry, the fact that H2 is 0.
So can't you just blow up and get a zero map? I mean, you blow up the ambient manifold or something. I mean, the proof of that result is you want to show that the not filtrations are preserved on the chain level. And I believe we did use the homological conditions.
More questions? All right, let's thank Andras again.